2 of number theory. And so today we're going to do GC, LCM. We're going to do a quick review on factorials. We're going to cover some bases. Then we're going to move on to the units, digits, and the significance of it. Then we move on to repeating decimals, and finally, modular arithmetic. Now let's try to figure out how to solve LCM, or least common multiple. So, as it says, we're trying to find all the multiples of 12 and 15, and we want to find the smallest of them. The smallest. Because we can't find the biggest because there's infinitely many numbers. Anyways, so our first method is to list out all the multiples. 12, 24, 36, 48, 60 for 12, 15, 30, 45, and 60 for 15. And we have 60, which is in common for both of them. Therefore, it is the least common multiple. Now let's try a quicker, easier method. We try and factorize them again. That's why factors are really important. So for 12, we have 2 squared times 3. 15, we have 3 times 5. So we circle all the ones that they have in common, which is 3 in this case. So we only write it once. Everything else we write as it is. So we do 2 squared times 3, and we only write one of them, times 5, which is 4 times 3 times 5, which is 4 times 15, which is 60. Second topic, which is factorials. And you probably already know this because we studied it in our combinations and permutations part. But here's a quick review. If we have something like n factorial, that is basically n times n minus 1 times n minus 2 times n minus 3 all the way to 1. For example, if we have 5 factorial, that is basically 5 times 4 times 3 times 2 times 1, which is 120. And if we have 3 factorial, that's basically 3 times 2 times 1, which is 6. Basically, when you have a factorial, you're multiplying all the numbers before it in itself. And one last quick thing, 0 factorial is 1. Now we move on to our third topic of today, which is bases. And the current numbering system we have today, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, is called base 10. And we use it all the time. And fun fact, it's base 10 because we have 10 fingers, and that's why it's 10 instead of like 8. Maybe if we had 8 fingers instead, we might use base 8. But no, we're using base 10. So what is base 10 really mean? Let's say we have a number 123,456,789. Well, we can rewrite this as 1 times 10 to the 9th plus 2 times 10 to the 7th. This is supposed to be 8th. 1 times 10 to the 8th plus 2 times 10 to the 7th plus 3 times 10 to the 6th plus 4 times 10 to the 5th plus 5 times 10 to the 4th plus 6 times 10 to the 3rd plus 7 times 10 to the 10 squared plus 8 times 10 plus 9 times 10 to the 0th power. And basically this means 9 plus 80 plus 700 plus 6,000 plus 50,000 and moving on. So that's technically what base 10 is. So you might be wondering, are there any other bases? Well, yes, there's infinitely many bases. And let's try an example. Let's say we have the number 5,763 base 8. And we want to figure out what it is base 10. Well, we're going to apply the same logic we did for this. If we have a 3 here, that's going to be 3 times 8 to the 0. If we have a 6 here, it's going to be 6 times 8 to the 1. 7 here means 7 times 8 squared. 5 here means 5 times 8 cubed. 0, 1, 2, 3. 8 to the 0, 8 to the 1, 8 squared, 8 cubed. And so, when we do this, we get 3,059 as our answer. And that is 5,763 base 10. So let's say we want to convert a base 10 number to a different base. For example, we want to change 27 to base 4. Well, what we're going to do is we're going to apply a bit of logic, multiplication. So we're first going to think, what is the highest power of 4 that is less than 27? In this case, it's 16. And so we're going to do 1 times 4 squared, which is basically 16. And then we think, what is the next highest power? It's 4. And after we do 27 minus 16, we're left with 11. So we do 11 minus 4 minus 4. We can fit 2 4s in there, so we're going to do 2 times 4, which is right here. And then we think, we have 3 left over now that we did 11 minus 4 minus 4. So let's just multiply it by 4 to the 0, which is 1. So we do 3 times 1, which is 3, and we get 1, 2, 3. So 27 is 123 base 4. And one last thing is, if we want to convert, let's say, base 8 to base 4, I wouldn't know why you would do that, but you always want to go from base 8, convert that to base 4, base 10, and then take base 10 and convert it to base 4. So you always want to use 10 as like the middleman to the units digit. And as a little warm-up, I want you guys to do these 3 problems. But wait, you might be like, do I have to do all of these? Well, there's an easy way to do all 3 of these in the snap of your fingers. I can't snap, but yeah, I still can't snap. Anyways, so you might be wondering how I know that this first one is B with not doing any work. And no, I did not look at the answer. I literally am doing this right now. Or how I know this one is A and that this one is also A. Well, the answer is the units digit, as the title says. So you might be wondering, how is such an insignificant number super good? Well, here's why. If you look at the units digit of these two and multiply them, you get 28. And the last digit, if this is 8 and this is 6, therefore our answer is B for the first one. For the second one, what is 600? What is this squared? Well, 6 squared is 36. And so this ends in a 6, therefore that is our answer. And which of the following is a perfect square? Well, we can't have, no squares will ever end in 2 or 3. So our answer is A. Here are some quick tips that will help you in any kind of math competition, including math counts, AMC 8/10/12, or math counts. So if you're trying to find the units digit of the sum of 2 things, just add the units digit of those 2 things. If you're trying to find the units digit of a product of 2 things, just multiply the units digits of those 2 things. Perfect squares. The units digit will never be 2, 3, 7, or 8 in a perfect square. So remember that. That is because all the others, like 1 squared ends in 1, 2 squared ends in 4, 3 squared ends in 9, 4 squared ends in 6, 5 squared ends in 5, 6 squared ends in 6, 7 squared ends in 9, 8 squared ends in 4, and 9 squared ends in 1. So 2, 3, 7, or 8 never appear. And if you have exponents and they're asking, what is the units digit of 1079 to the 87th power, you just want to find a pattern. For example, for number 9, a pattern you can find is that if there's an odd exponent, it ends in 9, such as 9 to the 1 is 9, 9 cubed is 729. I'm not going any higher than that. And even ends in 1, such as 9 squared is 81, 9 to the 0th power is 1. And you can find many patterns like these in any number that you try. So look out for those patterns. So now let's move on to repeating decimals. And basically what we're going to do for this today, it's just going to be a short review on how to convert from repeating decimals to fractions and fractions to repeating decimals. Well, let's start with 1 over 9. Basically, that if you just put it into a calculator is 0.1 with 1 repeat. Or another way you can know it is repeating decimals always have nines underneath. And so you have 1 over 9, and then you just repeat the 1. That might be a bit confusing, so let's try another example. If you have 0.857 repeating on, and you want to turn it into a fraction, what you're going to do is take the repeating part, which is 857, and you're going to put it over the same number of 9s that it has. For example, if it was 0.857, you would put it over 4 9s. But since there's only 3, you're going to do it 857 over 999 and simplify it if necessary. But it's not necessary. And then, let's say you have 235 over 999. Basically, we see that there's 3 9s Therefore, this part must be the thing that's repeated. And so you get 0.235. Now let's move on to our last topic of today, which is modular arithmetic. And whenever you think of modular arithmetic, you should think of the word remainder. So one thing about modular arithmetic is that if two numbers are considered congruent if they leave the same remainder. So here are some examples of what happens in modular arithmetic. If you have 13, 13 is technically congruent to 1 mod 12. 5 is congruent, there should be another line there, to 2 mod 3. And basically it means when you divide 5 by 3, it leaves a remainder of 2. When you divide 13 by 12, it leaves a remainder of 1. And modular arithmetic numbers are usually written in the form n with 3 lines, sorry about that, is equal to the remainder of mod m. M is a random number, n is the number that you're dividing m into, and r is your remainder. So our first problem of today is, what is the sum of the first 2011 digits when 20 over 11 is written as a decimal? Well, so what we're going to do first is rewrite 20 over 11. And we're going to rewrite this as a mixed fraction, which is 1, 9 over 11. And as we learned in the repeating decimal review part, we want our denominator to be consisted of lots of 9s. And so we're going to rewrite this, we're going to multiply top and bottom by 9 to get 1 over 81 over 181 over 99. So in the end, this is going to be rewritten as 1.81, and this part is going to be repeated since these two are 9s. So they're asking for the sum of the first 2011 digits. Well, this is our first digit, and it repeats 81, 81, 81, 81. And the sum of all those 81 pairs is 9. So we're going to do 9 times 2010, because this is a digit, over 2, which is equal to 9 times 1005, which is 9045. But then we have to add that 1. So our sum is 9046, which is our answer. Our second problem is the following. Which of the following is divisible by 6? A, 1 million minus 1, B, 1 million minus 2, C, 1 million minus 3, and D, 1 million minus 4. So we're going to think back to the last video on senior intermediate where we go over our divisibility rules. So for 6, it has to be divisible by 2 and 3. And for a number to be divisible by 2, it has to be even. For a number to be divisible by 3, the sum of digits have to be divisible by 3. So we're going to go through all our options and start off by eliminating some. So 1 million is an even number because it's 1, 0, 0, 0, 0, 0, 0. It ends in 0. So if you subtract 1, it's going to become odd. Therefore, it won't be divisible by 2. The same goes for 3. Now we're left with 1 million minus 2 and 1 million minus 4. So let's write these out. So we have 9, 9, 9, 9, 9, 8, and 9, 9, 9, 9, 9, 6. These are these two. And so when we look at this, we want our sum of the digits to be divisible by 3. So if you look at these first 5 digits, they're already divisible by 2 because it's basically 9 plus 9 plus 9 plus 9 plus 9, which is 45. 45 divided by 3 is 15. And so we're going to look at our units digits in this. And we're going to see which of these is divisible by 3. 8 isn't divisible by 3, so therefore our answer is D, 1 million minus 4. And now for the last problem of today. What is the smallest possible answer for which the following is true? 1, it's odd. 2, it's not prime. And 3, the next odd after it is not prime. So let's start off with number 1. These are all odd. Yep, they're all odd. None of them end in 0, 2, 4, 6, or 8. And then let's move on to non-prime. All of these are not prime. 9 is divisible by 3, 15 is divisible by 3, 21 is divisible by 3, 25 is divisible by 5, and 33 is divisible by 3. So now let's move on to our last one. The next odd is not prime. That means the prime after isn't odd. The odd after it isn't prime. So 9, the next odd is 11, and that's prime. 15 moves to 17, which is prime. 21 to 23, which is prime. 25 to 27, which isn't prime. 33 to 35 is not prime. So then we're stuck between D and E. Is it 25 or 33? But then this is where you guys have to look back to the problem it says. What is the smallest? So our answer is D. Don't forget to subscribe and like. If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!